In this video, we are going to review enamine formation. Now, to form an enamine, you have several requirements. You need a ketone or an aldehyde. You need an amine with two substituents exactly, and you need a catalytic amount of hydrogen. Hydrogen concentration cannot be too high. It cannot be too low. You need catalytic hydrogen, maybe a pH of about 6. Anyway, how does this work? Well, the first step is attack of the nitrogen on the carbonyl carbon. You don't need protons for this step. It'll go without the protons. And you form a tetrahedral intermediate. Okay, now this tetrahedral intermediate is, of course, zwitterionic, and let me just move the hydrogen here a little bit more so we can see the bond clearly. So the first step is going to be transferring that hydrogen, that proton, over to the oxygen, forming a hydroxyl group. So we'll just do that simple transformation. Okay, and this gives us this species. And we're all set up to kick out that hydroxyl, but it turns out it's really not a good enough leaving a group. So what you have to do is to protonate it. And let me just make a little bit more room here. We're going to protonate it, and this is why that catalytic hydrogen is needed. So let me go over here and grab some of those protons. Okay, and we're simply going to protonate the oxygen here to set it up as a leaving group. And give us this species. Now this is now all set up for the elimination. And so the elimination is going to be the lone pair of the nitrogen comes forming a double bond, kicking out, well, I drew that bond the wrong place, so arrow the wrong place. I pointed at the atom and not at the bond. You got to be careful about things like that. So let me try again. Nitrogen to the bond. Okay, now I want to kick out the water. Okay, draw my reaction arrow, and we should have our product. So there it is. Okay, so the water is off screen, I think. Yeah, there's the water hiding over there. Let's just bring it back on here so we might remember that we have it. I'll go back bigger again. Okay, so now we want to get rid of that positive charge on the nitrogen. And to do this, we're going to kick out a proton, and the proton we're going to kick out is on the ring, and so we just need to draw in a proton, and we're going to form a double bond there, and shove the electrons out onto the nitrogen, and so this will give us our final enamine. So there's the enamine. Well, that's all well and good, but let me run through this again with another situation. What if we had a methyl group on the cyclohexanone up here? Now, if we had a methyl group on the cyclohexanone up here, when we get down, let me just erase this arrow here. When we get down here, okay, we will have a methyl group there. So, and of course, that would give us, the way we've drawn this, that would give us a methyl group there. But you say, the hydrogen next to the methyl group is actually, would lead to a more stable alkene, or at least it would be higher higher substitutions on that alkene if we do it from this side. So what happens if we take this hydrogen and form the double bond, pushing the electrons onto the nitrogen? We're going to go down here. We'll get an alternate situation where we've got a new enamine candidate. So with a methyl on the one side, we have choice. Which one do we make? Well, you'd say if thermodynamics wins, it looks like the more highly substituted alkene would win. But wrong. It turns out the less substituted alkene wins. How can we understand this? Well, what it has to do with is steric hindrance. Down here, in fact, both cases, the nitrogen's lone pair takes on lots of p character and wants to delocalize into the double bond. That does a couple of things. It forces the nitrogen to strive toward planarity, and when it does that, it means this whole system becomes planar. which means there starts to be significant steric hindrance between the methyl group here and the ring. Up here, the only thing that we have to worry about on the double bond is a hydrogen. So we still have steric hindrance between the hydrogen and the ring, but a hydrogen's a lot smaller than the methyl. So this steric hindrance across between the nitrogen substituents and the methyl makes this less stable than the one up here. So the general rule in forming an enamine, you make the least stable, you make the least substituted enamine, the least substituted enamine. And that's going to be a rule which we're going to use as we now turn and say, what can we do with these enamines? How can we use them in synthesis?